Hello everyone. We will now introduce the concept of geometric sequences. By definition, a geometric sequence is an ordered list of numbers where each term, other than the first, is obtained by multiplying the number that precedes it by a fixed value r that we call the ratio. Now, more likely than not, we will be using r values that are not zero, otherwise every term would be zero in the sequence, and that are not 1, otherwise the sequence would just have the same number repeated over and over again. For example, the sequence of numbers 3, 6, 12, 24, etc. is considered geometric with a first term of 3 and a ratio of 2, since every number is doubled compared to the one before it. The sequence 2 minus 6, 18 minus 54 is also a geometric sequence with 2 as its first term and a ratio of minus 3. In both cases, observe how the size of the terms is growing and will obviously become infinite, or in the case of the second sequence, will alternate between positive and negative and with growing size. The sequence of numbers 3, 1, 1/3, 1/9 is also geometric with a first term of 3 and a ratio of 1/3. 8 minus 2, 1/2, minus 1/8 is geometric as well, with 8 as the first term and a ratio of minus 1/4. So this time, both sequences that are shown above have sizes of terms that shrink and will actually converge towards 0. So in terms of notation, we're usually going to denote by A0, A1, A2 the terms of the geometric sequence itself. So A0 will play the role of the original term in the geometric sequence. A1 will be obtained from A0 by multiplying it by r, the ratio itself. So in other words, A1 will always be A0 times r. Likewise, A2 is obtained from A1 by multiplying it by r. But that really is equivalent to obtaining A2 from A0, and where we have multiplied by r 2 times, so A0 times r squared. So actually, if we examine the pattern developing here, A0 is the first term, A1 is A0 times r, A2 would be A0 times r squared, and you can probably guess that A3 will be the result of A2 multiplied by another ratio called r, so A0 r cubed. And in short, we can observe that any term of a sequence that is geometric can be obtained without explicitly having to write out the entire list. In fact, the term in the kth entry, in the kth position, will be equal to A0 r to the power k. Now for clarity, we occasionally use accolades to denote a sequence. So for example here, notice that I've used these curved parentheses that we call accolades. A0 r to the k is the formula that we use to find all of the different terms of the geometric sequence. K equals 0 to n are the bounds of the sequence. So what is the first value of k that we replace in the sequence and the last one? So as you can see on the right-hand side, A0 times r is what is obtained when k is replaced by 1. When k is replaced by 2, A0 r to the power 2. And according to the upper bound n, we would stop at A0 times r to the power n. We can explicitly just write the values that are taken. So A0 r to the power k, so the general rule we're using for k values that are 0, 1, 2, 3, ... until n. So this would also produce the same sequence of numbers. For instance, the sequence 3, 6, 12, 24 that we presented earlier has an initial value of 3 and a ratio of 2. So a general rule to express the sequence would be AK. So the kth term of a sequence is always obtained from 3 times 2 to the power k, where k starts from 0 and 1 and 2 and so forth. And if you want to test it on your own, you can actually try replacing k by 0, by 1, by 2, and observe that we do get the terms 3, 6, 12, 24, and so on. If we examine where this sequence is heading, so if we think of what happens if we replace k by growing numbers, then clearly the limit of these AK terms of the sequence does not exist as they are heading towards infinity. Likewise, for the second sequence we presented earlier, 2 minus 6, 18 minus 54, a general rule that we could use to express the terms of the sequence is 2 times minus 3 to the power n, 2 being the first number, minus 3 being the ratio being used, and n is replaced consecutively by 0, by 1, by 2, and so forth. So once again, the long-term trend of this geometric sequence, so if we look at where these terms are heading, well, actually the limit simply does not exist, because the terms are first of all growing, and secondly alternating between positive and minus signs. So we can't even tell if it's going to infinity or minus infinity because of the alternation. Now, in contrast to that, we have a geometric sequence whose terms are decreasing. So in this case, we have a first value of 3 and a ratio of 1/3. So we could express the general rule for the geometric sequence as Cm. So basically the subscript m just means, or refers to the position of this term in the sequence. 3 plays the role of the A0, or the C0 in this case. 1/3 would be the R, and m is changed by or replaced by 0, 1, 2, 3, and so forth. In this case, the terms of the sequence actually go to 0, and you can tell by the fact that the sizes are shrinking. Every term is 1/3 of what it used to be. Similarly, the alternating sequence with 8 as the first number and minus 1/4 as the ratio can be written in a general form, di, so I here is the variable and refers to the position. So 8 times 1/4 to the I, and once again, because the ratio is less than 1 in size, the terms are shrinking and will eventually head towards 0. So to summarize, you'll notice that any geometric sequence whose general form is A0R to the K will either head towards 0 if the ratio is between -1 and 1. If it's positive, then the terms will be positive and simply go towards 0. If the ratio is negative, it'll alternate, but the size will shrink. Or if the ratio is bigger than 1, then the terms grow and eventually will go towards infinity. So there's no limit per se to the sequence. And the limit does not exist either if the ratio is -1 or less, because of the alternation of signs that will take place, as well as the fact that it might grow to plus or minus infinity.